before. While I'm thinking of it too, and I probably will say something on Friday. This is Wednesday, right? On Friday. So Friday actually is an opportunity for public viewing at the observatory again. I think it's going to be beautiful weather Friday. So sounds like a road trip to north of Burlington to the Whitty Observatory to earn lab credit. And I will be up there on Friday. So what time? Like when it gets dark, I'm thinking like you can come early. I'll probably be there like 7:30 or so, but when it gets dark, it's like 8, I'm thinking. So, yeah, and you can definitely bring people with you. And
are we just all driving our own way, or is it like a bus?
Yeah, you're just all driving your own way. And kind of generally, like, if, of course, you guys would take Highway 61, I'm thinking, right? Okay, so if this is Highway 61, okay, then you go through Burlington. You stay on Highway 61, right? Now, if the next town you get to from Highway 61 would be Mediapolis, okay, if you get to Mediapolis, you've gone too far. So basically, between Burlington and Mediapolis, there actually is a John Deere dealer right here, J. Deere, okay. Over here is Sperry. There's a water tower and stuff over there. But what you want to do is you're going to turn right here, okay, and there'll be a brown sign that says Big Hollow Recreation Area. Big Hollow. Rec area. So the brown signs are kind of like the, parks and stuff. So follow the brown sign, and I think this is, I can't remember the name of that road. But follow the brown signs, and then about maybe 3 miles down here, you'll see another brown sign, okay, right over here. And then you'll need to turn this way. I think that's 152nd Street. I'm not sure. But you'll need to take one more one more left turn, 2 lefts. And then actually right here is the observatory. Are you thinking about coming up, Blake?
Maybe I have a wedding to go to, or wedding thing, like a recital.
Okay.
I'll try to.
Very good. Very good. Okay, so yeah, this is a review slide. This is a review slide, and the reason I want to show you this is because we're going to talk about Mars today. How appropriate. And actually, Rush Limbaugh, which, I don't know. Anyway, Rush Limbaugh, when he asked why Mars lost its atmosphere, we're going to actually talk about that, why Mars changed, okay? Mars has been in the news, of course, because it's actually seen flowing water, defined flowing water. So basically, if you take a slushie, you buy a slushie like at Dairy Queen, okay, and put it on an incline and let it roll down, that's basically what they've seen, okay? So that's their flowing water. One of the things about, have you ever heard of putting, I know this works, have you ever heard of putting salt on roads so they don't freeze so much? Okay, so actually if you have salty water, you have brining water, B-R-I-N-E, okay, brine. So actually, basically what's flowing is basically salty, icy water. So it's the freezing point has been what we say depressed, okay, so that's why it can be a liquid under the cold temperatures of Mars. So the reason that has to do with Mars, of course, this is not Mars, this is the Earth. But before we talk more about the Earth, I wanted to remind you of the Earth's protective magnetosphere, okay, the magnetic field that the Earth has. Okay, so what else do we need to know about the Earth? Okay, well, remember a few slides ago, I think of that gal with her silly putty, and she was so disappointed because if she pulls silly putty too hard, it breaks. Okay, actually, things can kind of reshape themselves over time. Rock can reshape itself over time if gravity works on it. But each one of these terrestrial planets, and we're focusing only on the terrestrial planets, actually have kind of different surface features. Remember we said that Mercury, the planet Mercury, and our moon look similar, like they're gray cratered. Like really, what's up with that? The Earth really doesn't have many craters and that sort of thing. Venus, we're going to see it's cratered, but not as much as it should be, actually. Okay, and we'll talk more about Mars' surface, too. But on the Earth, we definitely have, it's geologically active. Geologically active, what does that mean? It means you have volcanoes and earthquakes and that sort of thing. Volcanism and tectonics kind of go together. It's ooey gooey. So volcanoes, of course, can resurface it. Tectonics can resurface it. We have a couple of different types of erosion. We have wind erosion and we have water erosion. So these are all things that the Earth's surface is kind of reshaping itself. So starting with the craters. This is just kind of a drawing. The left one is actually kind of showing you when a crater is formed, what causes that. And actually it's just space debris hitting the planet or the moon, okay? And it causes this crater. This here, this middle picture, actually it's a photograph, Winslow, Arizona, just like the song goes, okay? It's a big, humongous crater that it's relatively recent, and that's why it has not been resurfaced. What do I mean by recent? 50,000 years, all right? Okay, so volcanism. So here we have a volcano going off. This is just I think it's a figure, not a photograph, okay? And of course the lava can go ahead and resurface Earth, surface features. This actually is Mount St. Helens, a photograph of Mount St. Helens. So we don't necessarily see the flows that we do like on the Hawaiian Islands with the magma coming out, the lava flowing. But here you can see Mount St. Helens. It really affected Earth because of a lot of the particulates that it put out. Closer to home than Mount St. Helens, do you remember like a couple years ago, Greenland had an active volcano. It spewed ash, and actually it played havoc with people wanting to fly, okay? So that sort of thing is actually a player in the Earth's atmosphere and as a player in the Earth overall. So this is looking at erosion. From left to right, we have river erosion from the Grand Canyon. The middle one, the B there, is actually talking about erosion that glacial ice can cause as it comes down and retreats, The C is wind erosion, okay? And D is just kind of sedimentary being relocated from at the exit of a river. So we definitely have these. So when you think of the other 3 terrestrial planets, Mercury, Venus, and Mars, you're like, not so much, right? So with regard to tectonics in general, this is how tectonics work. Now, you might recognize these when we talked about how is heat transferred from the Earth's core outwards. We talked about these kind of convection cells. That's exactly what those are. So basically, all the planets are hottest at the center, okay? And so, and we still have an ooey gooiness to us. So basically, that hot liquid mantle rises because it's less dense, and then it cools as it rises, and then it will sink, forming these kind of convection cells, which take, 100 million years or something like that? Or no, a long time for it to complete one cycle. So anyway, in doing so, those cells, we can have a couple of things that go on with regard to these plates. So up here we have kind of a couple of plates, okay? And here we have plates that are coming together, okay? Because why? Because the cells are actually coming together, okay? Converging plates can create mountains. Diverging plates here, actually, because the cells are moving away from each other, okay, can cause a different feature. Seafloor spreading or subfloor spreading. So the Earth's atmosphere, now this is different than the Earth's magnetic field. The Earth's magnetic field, called the magnetosphere, that's after the Earth's atmosphere. Here's the Earth's atmosphere, and it's pretty darn thin. One of the things I think that I've seen pictures from space, and maybe you have too, looking back at the Earth, and you're like, that's how thin our atmosphere is. Okay, it's pretty precious. But right now, its composition is about 80-20, 80% nitrogen and 20% oxygen, and it hasn't always been like that. Here in our atmosphere, we also have water vapor, carbon dioxide, which of course carbon dioxide, we're like, Carbon dioxide isn't there in a great amount, but carbon dioxide, the gas, actually can have a warming effect, and we're going to talk about that. So this kind of reminds me of the slide we looked at before. The slide that, remember, why do you put a telescope in outer space? Well, this is why. Because basically, Earth's atmosphere blocks some types of energies. So this is kind of what this reminds me of. Specifically, you guys have heard of the ozone layer, okay? The formula for ozone is actually, it's got 3 oxygens stuck together. So the formula for ozone is O with a subscript 3. Now, ozone is in what we call the stratosphere. But the deal about ozone is it's specific for the energy coming from the sun in ultraviolet region of the spectrum. So the word sterile here should scare you. Sterile, of course, means that, if you sterilize something, it means you kill all the little microbes, okay? So as far as we know it, Mars right now, well, shall I mention it, is actually sterile, okay? And part of it is it doesn't have an atmosphere, okay? Life as we know it actually cannot walk around on Mars unhindered because it would basically be irradiated, okay? Doesn't mean we're not looking for past life. And we'll talk about why Mars has kind of evolved the way it is now. Yep, we need our atmosphere. So there's that pesky little lambda. Remember, lambda is the symbol for wavelength, okay? So actually, I want to kind of just briefly say why, when we walk out on a sunny day, why we don't look up at the sun, never look at the sun, look near the sun, and why it doesn't just look like a star with blackness around us. Honestly, if you were to be on the moon and look at the sun, never look at the sun, but if you were to be on the moon and look at the sun, the skies would be just black. So you'd be black sky and the sun, okay? So it has to do with the Earth's atmosphere, and it has to do with wavelength. So here we have a couple of scenarios. Now, the thing, we talked about Roy G. Biv. I'll kind of write it down here at the bottom here. Roy G. Biv. Oh, my gosh. She says that one more time. Of course, that actually is the mnemonic device to separate the colors of light where R is red and V is violet. Okay, and as it turns out, actually, we have the most scattering here. Of course, this would be the short wavelengths. Okay, so the short wavelengths of light coming in are scattered by the Earth's atmosphere. Recently, again, it's all about Mars these days, but we definitely have rovers on Mars that are taking pictures, continuously sending them back to us. And the Martian day has a different cast to it. The skies aren't, during the daytime, it's not like black and then you see the sun, because Mars does have a little bit of an atmosphere, but the chemicals actually then cause a different type of scattering. So this is the scattering we get. Now this, I like this figure because this guy right up here, basically he is when the sun is directly overhead. When the sun is directly overhead, you have this scattering. You kind of see the blue being scattered out, the red coming straight through. When the sun is overhead, it doesn't have much of the Earth's atmosphere to go through. This guy right here, okay, actually the sun is low on the horizon there. Okay, it's not overhead, it's low on the horizon. Okay, and so we have this scattering out to the point of basically removing the blue color. See over here? There's no blue color that gets to this guy when the sun is low on the horizon. If you've ever, in the morning when the sun is low on the horizon, or in the evening when the sun is low on the horizon, look at a speed limit sign, okay, or something that's white, okay, it like glows red or orange. Basically what's happening is the light that's coming from the sun, the blue is removed and all you're getting is the red and the orange, because there's more of the Earth's atmosphere. Okay, that's called Rayleigh scattering. Let's put it up there. That's why the daytime skies are blue and the morning and evening skies are red or orange. Rayleigh, I think that's how you spell it, scattering. Cool. Okay. So in this unit, actually, we're going to finish up talking about other stars and how other stars actually have planets orbiting them. And there's a big search to find a planet that is habitable, as we know it, right? My thing is, and maybe you've kind of seen these documentaries on too, where there's these things called extremophiles, where life can actually live in really extreme conditions, like really hot or really cold, really dry, really wet, okay? But habitable temperatures to us. Now, the Earth's temperatures are good. Earth's temperatures are habitable right now, okay? Did Mars used to have habitable temperatures? Maybe, okay? Does it have habitable temperatures now? As it is, no. Actually, I have a t-shirt that says Terraform Mars. If you're not kind of familiar with the science fiction idea of taking a planet and then conditioning it so it's like Earth, okay? But the Earth's temperature and the temperature of the other planets is affected by actually what's in its atmosphere. So I mentioned we have some carbon dioxide in the Earth's atmosphere. So I don't mean to get up on my soapbox or anything, but the whole thing about carbon dioxide, actually, carbon dioxide is a product or produced when we burn fossil fuels like gas and coal and that sort of thing. So the amount of carbon dioxide in the Earth's atmosphere has been increasing since the Industrial Revolution. But anyway, so carbon dioxide in the Earth's atmosphere, it is one of the gases that can actually act as a greenhouse gas. So this figure is trying to kind of show you how greenhouse gases work. Greenhouse gases are kind of like a greenhouse, in that what a greenhouse does is you have glass or some sort of very clear plastic that allows visible light to come in. So the visible light here is the yellow, visible light from the sun. Okay? In your greenhouses and on the Earth, what that visible light does is interact. We talked about how energy can interact with matter. It interacts with the Earth, actually, and the Earth absorbs the energy, and it turns it into thermal energy, heat. Okay, so here we have light coming in, and basically the Earth heating up, just like a greenhouse. Light comes in, stuff in the greenhouse heats up. The thing about thermal energy and your greenhouse or the Earth's atmosphere is that the thermal energy does not like to leave. So here you see the red lines are thermal energy, and you see it interacting with the greenhouse gases in the Earth's atmosphere. Okay, so basically what comes in, interacts, isn't leaving because it's a different form of energy. And that's kind of what happens in your greenhouses too. It happens in your car, right? On a cold day, if it's a sunny day, you have light coming in, interacting with your black upholstery, right? Okay, absorbing that energy, turning into heat. Does it go out? Well, some of it, but actually glass is a pretty good, not bad insulator. Okay, so a lot of that thermal energy is trapped. So that's exactly in a nutshell what's happening. Now, to be fair, these greenhouse gases that are kind of interacting with these red here, this thermal energy, greenhouse gases are carbon dioxide. Actually, water vapor is a greenhouse gas. Methane that actually cows produce in their digestive system is another greenhouse gas. So we have other things other than carbon dioxide that's in our Earth's atmosphere doing that. But I like this figure over here, because this figure over here, and we're going to talk about more planets other than just the Earth coming up. But it says, let's consider some of the other planets and their atmosphere and how they add to, because of the greenhouse effect, change their temperature. So starting with the Earth here, right? So if we did not have a substantial atmosphere to go ahead and kind of be a blanket in a sense, our surface temperatures would be about negative 16 degrees Celsius. Our surface temperatures would be without the greenhouse effect. So sometimes one of the things I like to emphasize is, do we need the greenhouse effect? Yes. Is the greenhouse effect getting more enhanced? Probably. Okay. So as it is, we have 31 degrees warming because of our gases, our atmosphere. And so if you add 31 to negative 16, you get 15. So that's where we're at. Okay. So we're about 15 degrees Celsius. So my night class, somebody said, well, how cold is negative 16? Well, I think cold. You figure water freezes at 0 degrees Celsius. Okay, so kind of back down from there. So that's the Earth. So if we look at Venus now, one of the things I've already said about Venus, we'll talk more about it, but I said it has a thick atmosphere and it has a lot of carbon dioxide. Okay, so actually look at the sort of warming it has with its atmosphere. Oh my gosh. It has 510 degrees Celsius bumped up because of its greenhouse effect. Like, okay. So instead of being negative 40, okay, it's running surface temperatures about 470 degrees Celsius. That's a little toasty. Some would say actually kind of that the Venus has a runaway greenhouse effect. You know, that I would agree with, okay? And it's just chocked with carbon dioxide. Okay, so looking then at Mars, Mars doesn't have much of a greenhouse effect. Why? Because actually the atmosphere that Mars has now is not what it used to have. We'll say, why did that happen? But there's just not much there to bump up its temperature, so it's a bit chilly on Mars. Who's going to go see the movie The Martian? I so am. Yep. I think we all should. Okay. I thought about making it worth lab credit, but I just can't do it. It was so close. I know. The Martian. It looks really good. So I'm hoping this comes up. I want to show you to kind of get a sense for the planets and as far as missions to the planets. Okay, this is an infographic to show you how we visited the planets. So when that finally comes up, remember I said how busy Mars is? Oh my gosh. Mars has like all this activity visiting Mars. Mercury, as far as I know, cute little Mercury, has only been visited, I think, 2 missions. Okay, and the messenger missions. It's coming. No, it's not, because it's in this weird mode. Mariner, I guess. There we go. All right. So and I saw this actually or something like this when we went to the Adler Planetarium in Chicago, which is a great place to go. But each one of these lines represents a spacecraft that has visited the planet. And so you see 2 around Mercury. Notice we've had 8 missions to the sun. Okay. And then kind of coming down. Okay. Venus, lots of flybys. Okay. But actually, as far as I know, I said there's only 1 space probe that's landed on Venus and sent back pictures. Okay. The Earth, okay, this one with all these lines around it, that's actually the moon, right? I buy that. Lots of missions to the moon, and of course lots of missions to Mars. Okay, so here we have Mars. Also, there's been some missions you probably know, maybe don't know, but we've studied, sent spacecraft to asteroids. We have successfully sent a spacecraft to comets, landed them on comets. These are the missions around Jupiter. Okay, then Saturn here, and some of these are kind of in transit. Okay, then of course we have the blue planets. Not much done with Uranus and Neptune. Okay, so the Voyager spacecraft, Voyager 1 and Voyager 2. Actually, they were great successes. They are actually, and they have little, you know how you send a message in a bottle? Okay, that's kind of what we've done with these spacecraft. I think it was Carl Sagan's idea. Basically, there's like a little record of humanity on these spacecraft that are leaving the solar system. I think that is so cool. It's like calls, right? Okay, so that's the Voyager spacecraft. And then...
I have a question.
Uh-huh.
I saw one on Jupiter that said they intentionally crashed it into it.
intentionally crashed into it yet.
Yeah, why'd they do that?
To gather data as it crashed, and or sometimes they crash things, so I don't think this would apply, but they crash spacecraft so it doesn't harm something else. They just know it's going to crash anyway. But which one? Oh yeah, Galileo. I think so. We'd have to look that up. But I think as it fell through, it was equipped with equipment to send us back some good data. That's kind of sad. Yep. So.
Billions and billions of dollars just being crashed on purpose.
Some really, really important things they found out
yeah.
though. But yes. I agree. This doesn't have to do with Jupiter or anything, but sometimes our satellites, or expensive satellites that orbit the Earth, I don't say intentionally, but they crash, right? And hopefully you're not there where they crash, when they crash. So I just kind of wanted to give you a sense for that. That's pretty cool. Okay, so starting with Mercury, kind of comparing side-by-side images of Mercury and the Moon. Not only do they both start with the letter M, but they look very similar. Okay, so they kind of have this pocked mark to them. You might recognize, here's the Moon and here's Mercury. The fact that you can actually even see craters. The Earth, we don't look around and see craters. Although I think there's a crater, they aren't as fancy as Winslow, Arizona crater, but there are craters here in southeast Iowa. I have to look that up. I have friends that said, yeah, you should go visit that crater. A lot of times craters these days actually have trees growing in them, you know what I'm saying? So, but the fact that you can actually see craters means that there weren't the stuff we talked about that resurfaced the Earth. So there aren't volcanoes like sending lava down to fill in those craters. There aren't plate tectonics, absorbing that stuff. There's no wind erosion, okay? So one of the things I kind of want you to get sense for is what their atmosphere is like. So already you know the Martian atmosphere is pretty thin, right? It used to be thicker. You know that Venus's atmosphere is very thick, okay? The Earth's got a substantial atmosphere. Mercury has a thin atmosphere, and the Moon basically has no atmosphere. Instead of having an atmosphere, the Moon is kind of oozing gases, creating what we call a temporary exosphere. I think that's kind of cool. All right, we haven't talked much about the Moon, but I kind of want to take one more stab at our beautiful Moon, which, oh my gosh, this morning you could see it. Did you guys see that? You could see the beautiful Moon. It's humongous. So if you're doing your moon journals, I'm just saying, it doesn't have to be nighttime when you fill in your blanks. So we talked about the fact that we only see one side of the moon, okay? We have the side of the moon that we see is the near side. The side we don't see is the far side. And the reason there is a far side, comic strip, is because actually it takes the moon the same amount of time to spin on its axis as it does to orbit the Earth. So on the moon, just kind of at a glance, you can kind of see these dark regions and these light regions. And these are things that I said, if you're looking for something scientific to include in your moon journal, you can talk about the dark regions are the mare, the light regions are the highlands. And as it turns out, and I'm going to kind of explain why, but those dark regions are actually kind of newer regions than the highlands. So the highlands are kind of like our old, I think of we have a couple of major mountain ranges. We have the Appalachian mountain ranges kind of in the east, then we have the Rockies in the west. The Appalachian mountain ranges are a lot older than, I think they're older than the Rockies. So sometimes you can actually see craters inside of craters. I'll kind of draw your attention to this kind of scenario here. You kind of see it was hit here, and wait, let me do that over. To me, it looks like this one is kind of underneath this one, to me. You can kind of get a sense for timing. The other thing is oftentimes they have these, what I call them belly buttons, like if I'm helping out at the observatory. But does that not look like a belly button to you? It's called a central peak, okay? So that's the central peak. It has terraced sides, so I don't know if you can see kind of it kind of just goes down, kind of like stair steps. Okay, like you would terrace that's kind of the terrace thing. Ejecta blanket, wow. A good example of an ejecta blanket is right here. So I'm pretty sure I got this right. I would call that Tycho. Tycho, like as in Tycho Brahe, we talked about before. The name of, oh, I didn't make it very big. The name of that impact site is Tycho. But can you see these kind of splashing outwards? Okay, that splashing outwards is basically when that impactor hit the moon, it basically it hit and stuff went up and it went flying in all directions. Okay, so that's the ejecta blanket. Okay, so you know we've been on the moon because we left our footprints. You know, people say we've not been on the moon, just. So I say that the moon is kind of like, well, you know that gravity is less, so you weigh less. And so, of course, that astronaut, wouldn't sink in. But the moon is covered with something like ash when you use charcoal in your barbecue, okay? And those briquettes, once they're done, they basically fall apart and they have this gray stuff. Okay, it's been a while since we've used briquettes like that, but that gray stuff is similar to what covers the moon, and it's called regolith. Okay, so regolith. That is kind of like the gray stuff on the moon. And Mercury, as far as I know, actually is kind of covered with regolith too. We've never landed a probe on Mercury, though. I like this term. This term, not all impacts are big. Some impacts are small. So actually micrometeorites are kind of what basically has kind of gone and kind of diced up and made all that gray regolith. So how did we get kind of these mare features? And it's kind of related to the moon's past geological activity. Now, when we think of geological activity, we think of volcanoes. Okay, so the moon never had volcanoes, but it was ooey gooey, had kind of liquid mantle. Okay, but it doesn't anymore. So kind of think of that liquid mantle in this sense, kind of going from left to right. I'm going to, ultimately on the right, you can see actually that dark region was an example of a mare. Okay, so this is a mare over here. That's the current mare. And kind of from left to right, what your author's done is kind of show you, oops, 3, 4, okay, kind of show you how you get mare. So this would be early on. You can kind of see all these craterings before the mare. Now this is early on when actually there was some ooey gooiness under the crust, the moon's crust. So picture basically it getting hit, okay? This is a relatively large crater. And right here, right here, it's thinned out. It's kind of close to the liquid mantle underneath. So kind of, it's so thinned out that actually that's why you got kind of the liquid from the moon kind of rose up and filled in those low areas. Then, of course, over time, it kind of radiated its thermal energy away. It cooled down. The moon's pretty small, okay, and basically it froze like that. So that's how we got the mare like that. Switching from the moon to Mercury, okay. So again, we have not landed on Mercury. The coolest pictures I've seen of Mercury, and I haven't emphasized this much, but so the coolest pictures I've seen of Mercury, if this is the Earth, okay, and we're going to put the sun over there like we have done before. And of course, Mercury and Venus, okay, orbit the sun closer to the sun as they orbit the sun. So actually, it's called a transit, where actually you see the sun disk here, and you can actually see Mercury go in front of the sun. It's a transit. Those are some of the coolest pictures. Or Venus go in front of the sun. So there are some interesting features on Mercury, including these hollow regions you see over there on the right. Mercury is pretty heavily cratered. One of the things about Mercury is that it has these kind of cliff regions. If you can kind of see this, I'll try to point out. This is kind of a cliff-like region right here. Basically, you'd straddle, you'd be low and high. And it's thought that these cliffs actually formed as Mercury cooled. Another cool feature about, well, there's a large impact crater on Mercury. All right. Finally, now, we skipped the Earth because we talked about the Earth. So, Mercury, Venus is coming up too. So going from Mercury to Mars. Okay. So the thing about Mars is actually, sometimes through a telescope, you can see these features. Okay, these are actually the polar caps of Mars. What this is trying to emphasize is a dust storm. On the planet Mars. Okay, so if there's a dust storm, a few things. That means there must be wind. You can get some wind erosion going. Okay, on Mars. That also means that you have loose material. Okay, flying around. So Mars is about half the radius of the Earth, about 10% of our Earth's mass, which means it's a lot smaller, isn't it? Okay, it's located, instead of being 1 AU, like the Earth is located from the Sun, it's 1.5 AUs. Let's see what this, I think this is an info, I think this is a photo to try to show you if it's gonna. The busyness around Mars. The craziness around Mars. So I'm hoping that this will show up okay. But I said it's a busy place, and I like what this person has done. One of the things about space missions, as you might imagine, is it's not just the United States doing it, and I think it's really cool that that a lot of times the space agencies will join together for a common mission. It's a very busy figure, but what they've done is to kind of, if you look at, see it says mission stages: launch, Earth orbit, transit to Mars, flyby, Mars orbiter, lander, rover, okay? And each ring is something, and you can kind of see the flags indicated by who did it. So it's pretty cool. It's a busy place. We talked about failed missions. I like what he's done, kind of scroll at the top there. If you see a circle that looks kind of like a splat, that means it was a failed mission. Where did it go? I thought it was this key. Like, do you see any splats? Yeah, malfunction. It's not really a splat, but right. This one right here, malfunction crash. It's just a busy place. I'm kind of like, I think we should like check out Venus more than we check out Mars. So, I don't know. Okay, so what else about Mars? Well, even though it's only 10% of Earth's mass, which, gosh, that's not much. Mars is only 10% of Earth's mass. It's got some similarities to Earth. For instance, its axis of rotation is tilted very similar, okay? Ours is 23.5. I think it's 24, 25 degrees tilt. It takes about 2 years to go around the sun once, though. The Earth goes around the sun once. It rotates on its axis. It takes about 24 hours, like the Earth. Okay, that's all cool. So we saw on the figure a little bit ago how much kind of greenhouse effect it has going with these gases, okay? It's gas that's gravitationally bound to the planet. It's mostly carbon dioxide, but it's pretty thin. Makes you want to go watch that movie and see how they handle that. Okay, it does have polar ice caps, but a lot of that solid that you see there is not like H2O ice. Actually, it's carbon dioxide ice. The reason it kind of has this red appearance is because of the presence of iron oxide, making it look red. So we said actually of the geologically active terrestrial planets, we said that Mercury, no. We said the moon, no. It's not a planet, it's not geologically active. We have a question mark for Mars. We said Venus is geologically active. Of course, the Earth is geologically active. So we have a question mark there. Notice there is some differences you'll read about kind of its northern hemisphere and its southern hemisphere with regard to kind of recent features. It has a large volcano called Olympus Mons. It's a dormant volcano. I have a picture coming up here. Olympus Mons is like they call it a caldera. Just got basically a big hole about the size of Missouri. So it has Olympus Mons, is a big caldera, expired or non-active volcano. And then the other feature that's cool on Mars, there's Olympus Mons. The other feature, and I think we talked about this before, I have another picture coming up, is that Valles Marineris. Oops. Yeah, Valles Marineris. That's basically a Grand Canyon feature. Goes like from our west coast to our east coast. And then the other thing, it's got this kind of strange sort of bulge called the Therius bulge. And that's in the dotted lines right there, Therius bulge. So this is the Olympus Mons, that caldera I was telling you about the size of Missouri. It's kind of got a plateau sort of thing going on. And this is the Valles Marineris, kind of stretches from coast to coast. All right, so water on Mars. So I have just a few slides about water on Mars, okay? And like I said, it's been in the news. People are really excited, except for Rush Limbaugh, who thinks we're lying. Oh my gosh, I don't know what you think about Rush, but he just is crazy. So he basically went on a rant about all that NASA has done is lie, 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 lie. So they're lying about this. I'm like, why would they lie about that? So he says that NASA's being manipulated by the government, which, I don't know. Anyway. So their surface features on the planet Mars say that water once flowed. And this is kind of an example of kind of something, an erosion pattern that could have been carved out by flowing water. But it wasn't until recently, and I'll go ahead and show you one article on it, it wasn't until recently that they have caught it in action. Now again, it's very salty, slushy sort of, I can't imagine drinking it, very slushy sort of thing, but it is flowing. So they've also done like experiments with their rovers to understand that Mars definitely has water vapor in its atmosphere, and Mars actually has ice under its surface to a certain extent. Okay, but some said that they did this kind of associated with the movie coming out. I don't know. I think that's a stretch. Okay. Let's see if this adds any. So those, when I said kind of that brainy stuff flowing downhill, this is a photograph of that stuff kind of flowing downhill. And they've kind of seen these for a while. And I mean, this is a photo from Mars. Okay, this photo from Mars isn't anything that new to me, but basically you can kind of see these streaks kind of change, and they would see that they would change color. I mean, not change color, but kind of change shape, like something's flowing, and that's exactly what's happening. So even before today, we had this other evidence, like I'm in a, court of law, okay? So, showing you like regions of like topography on Mars that suggests that it once had lakes, and you can kind of see the where the streams would have flowed. But I really like this one, kind of side by side. If you like, okay, so we have Mars on the left and Earth on the right. So if you've ever kind of gone and dabbled in like a stream, you see all those pretty pebbles, okay? And the reason they're nice and smooth, well, they're not all smooth, but because a lot of them have the smoothing down is because of water flowing. And so actually, Mars has pebbles. And of course, they're dry. I mean, there's a dry bedrock right now, but those pebbles were created by some sort of erosion, probably flowing water. Okay, so yeah, this one actually is the one figure from your textbook that we saw a minute ago on kind of why do we now know that there's water flowing on Mars. I'd say flowing is kind of a misnomer. It's more like just kind of sliding. Okay. So I think we've got time. One last thing I want to say, and go ahead and Twitter to Rush if you want to, but the reason that there must have been this change in the climate of Mars has to do with the fact that it's only 10% of the mass of the Earth. It's only 10% of the Earth's mass. So it cooled down more quickly. And this is what happened when it cooled down more quickly. Okay. So basically on the left you have what Mars used to look like. Okay, now the big thing here on the left is you see those pink, okay, those pink things. We saw those pink things around the Earth when we talked about currently the Earth's magnetic field, magnetosphere. So Mars used to have a magnetic field. What does something need to have magnetic field? It needs to be ooey gooey. It needs to have some sort of liquid inside. Mars cooled, it lost its magnetic field, and that's actually what you can see on the right here. When it lost its magnetic field, now actually these yellow things, that's actually energy or solar wind, stuff coming from the sun. Basically, the sun blew away its atmosphere. So down over here, we got the water, right? Okay. The atmosphere. All right, so that's about how far I want to get. Yay.